Now, as we have seen in the previous lectures that what is a spherical mirror all about, now we shall be trying to understand that what basically we mean when we say that this particular spherical mirror has got a very low aperture, which obviously means that the radius or the radius of the center of curvature to the pole of the mirror is quite large. What is it? We shall be seeing it with the light of an important concept of focus. Now focus as being it is a very important in the optics or ray optics. Now what basically a focus mean, or what is the focal length or the particular mirror? Let us try to understand. Now say for example we do check over here a concave mirror like this, and in this particular concave mirror we are not saying that it is not having a small aperture, which means that it is simply a concave mirror, right? Now as this is a concave mirror, obviously we can understand that this part is a reflecting surface. Now with the help of ray diagrams we shall be trying to understand this particular scenario. As we can understand that this is a principal axis, so obviously the center of curvature shall lie at, say for example, a point over here. Say for example this is the center of curvature C. Now we could say that let us make a light, an incident ray, which will obviously be nearer to this principal axis but parallel to the principal axis itself. Say for example the incident ray is like this. Now if this is the incident ray, then obviously at this particular point the normal shall be the radius of this particular mirror itself. So which will be the radius? Starting from the center of curvature to this point. So this will be the normal at this particular point. Now obeying the laws of reflection, reflected ray will actually pass like this, and if it passes, then we can obviously say that this angle of incidence, say for example if this is theta, this angle of reflection, this angle theta, will be equal obeying the laws of reflection. Now over here, if we could actually understand that if this particular incident ray is parallel to this principal axis, then this radius will actually act such that this particular angle theta over here will be equal to this particular angle. So this angle will also be equal to theta, as we can understand it with the help of geometry. Now let us give it some names. Say for example this is the point X. So we can understand that point X is that point on the principal axis where the reflected ray is actually meeting, and this is the reflected ray of that incident ray which is parallel to this principal axis, and obviously this incident ray is nearer to this principal axis, right? And let us say for example give it as the name of A. Now, considering this triangle CXA, we can actually enlarge this particular triangle to understand the concepts from geometry much more better. That's geometry as well as trigonometry. So, say for example, this is a particular triangle CXA, where this particular point is X, this is C, and this is A. Now, we can understand that angle ACX, this particular angle, will be equal to angle CAX, this particular angle, right? So, if this angle is equals to theta, this particular angle will also be equal to theta. Now, let us draw a line such that this particular blue line is perpendicular or normal to CA. And let us give this point as, name it as Y, right? Now, from this triangle, we can make out that there are two triangles now. Triangle CXY and triangle XYA, right? Now, it may be noted over here that triangle CXY and triangle AXY, they have got two angles equal, this theta and this theta. Also, this 90 degree is also equal to 90 degree, and the side XY, this is common to both these triangles. Now, we can obviously say that these two triangles are congruent, right? So, these two triangles are congruent triangles. Now, if they are congruent triangles, obviously now we could deduce another important fact, that this CY is now basically equals to AY, right? CY is equals to AY, and obviously if they both are equal, then they would just be the half of CA. Half of CA. Now, it may be noted that the CA in this particular triangle is basically equal to the CA, which is obviously the radius of this spherical concave mirror, right? So, again we could write it as CY is equals to AY is equals to the value of CA. Let us say, for example, this is the radius is R, then we can say it as R divided by 2, and let us give it as equation 1, right? Now, considering this fact, first of all, we need to understand that if this is R, then at what point from the center of curvature will this X be? So basically we need to understand that what will be this distance of CX, and the CX is basically this particular distance, so we need to find it out, right? Obviously, we have got the value of this base CY as equals to R divided by 2, and we need to find out this hypotenuse. So we will take the help of trigonometry now, and in trigonometry we basically know that over in triangle CXY, the cos value of theta will simply be equal to CY divided by the CX. Now, since we are actually interested to find out the value of Cx, let us find it out. That says value of Cx will now be equal to Cy divided by cos theta. Or in other words, we can write that Cx is equals to, what is the value of Cy? This is simply equals to R divided by 2. So this will be R sec of theta divided by 2. Now, from this particular thing, we can understand that this value of Cx will just be dependent on the sec theta. It will be directly proportional to sec theta. Now let us come to trigonometry. And as we know that the graph for sec theta, this will be like this, right? Now, if say for example, I am increasing the value of theta. Obviously, if the value of theta increases, then at this particular point, we can understand that the value of sec 0 is equals to 1. And if we are going to increase theta such that theta is greater than 0 but is basically lesser than pi by 2, then our graph will actually be confined to this region, this particular region. And if the theta, value of theta is greater than 0 over here, then it will be more than 1. Right? So the value of Cx will be equals to, at that particular point, will be equals to r divided by 2 multiplied by a factor. And this factor will obviously now be greater than 1. So, say for example, if theta is equals to 0, then this x point which has been found out, it will lie just this on the middle point between C and say P. This particular point is P. Because over here CP is also the radius, right? So, if theta is equals to 0, x will just lie at a point which is just the middle point of CP. But if theta starts increasing, then obviously we shall see that this particular Cx will start to move in this direction. So this will be the movement of this particular point x for a theta which is greater than 0, and obviously theta is less than pi by 2. Okay, so there will be a shift of x in this direction over here. Now, when it will happen that this theta is greater, this will happen only if and only if, first of all, that if, say for example, this is of large aperture, which obviously means that if we have kept an object which is very big, or say for example it is bigger than the radius of the center of curvature to the meter, then we can say that obviously this value of theta will be much more greater. But if it is not, what is the scenario then? It actually means that we are cutting out this particular piece of a mirror from the entire sphere that is very, very huge. Which obviously means that this particular mirror is a very small part of that particular big sphere. So it will seem as if this mirror tends to be a plane mirror. Mind my words, it tends to be a plane mirror, but it is not. Right? So in that particular scenario, we do say that yes, this has got a low aperture, right? And this particular scenario, when it will evolve, we will be seeing that any numerous number of rays, say for example this particular ray is coming parallel, say for example this is C, the center of curvature, and it passes through this point. Now another ray, say for example, which is again parallel to this principal axis, it will again pass through this particular point. Why? Because in this particular scenario, this mirror which is being kept is having a very less aperture, which means that this radius is very, very big. So we can say that these two incident rays are making such that the reflected ray is passing from this particular same point, and this point is basically this X. So we can say now that this point is F, where F is the focal point. Or simply known as the focus of a spherical mirror. Right? Now, say for example, if this is not the case, then what will happen? Yes, obviously, as we have seen, this will be the mirror, the concave mirror, and this will be, say for example, the principal axis over here. This is the center of curvature. And now over here we are trying to find out an incident ray which is obviously parallel to the principal axis. It will get reflected, say for example, from a point, and let us say for example this point is the focus. But mind it that if we are sending another parallel incident ray which is parallel to this principal axis, then obviously we shall see that this ray is passing somewhere like this. Now, as it was discussed over here, that if the value of theta start to increase from 0, we shall see this particular factor increasing, which obviously will increase the value of Cx. So over here, as we can see that if we draw two normals at these two particular points, we shall be seeing that this first normal over here at this point, this is making an angle of theta, whereas the other normal, which is basically made at the point of the other one, we shall be seeing this as phi, where obviously it may be understood, we could see it from geometrically, that here this value of phi will simply be greater than this value of theta, and if it happens, then obviously the factor for this phi will be greater than this factor of theta. Likewise, we can say that this C, say for example this point was X and this particular point was Y. Now we can say that since this factor is greater for this Cy, the Cy is greater than Cx. So if the aperture is not, say for example, less, where in other words we can say that this curvature is very, very high, okay, in this particular scenario we can say that yes, they are not passing, these reflected rays are not passing through the same point. And why it is so? This is because the theta, the value of theta is changing. But if, say for example, this has got a very low aperture, which obviously means that this curvature is not so much big, then we can treat that every number of phi or theta in this scenario will simply be equal, which obviously means that in this particular scenario, the normal which is drawn at this point and the normal which is drawn at this particular point, both are making an angle of say theta, right? So if the aperture is low, if the curvature of this is not as much big as like this, then obviously we can tell that this theta for all the scenarios are remaining same. And obviously if the theta remains the same, the factor will be just be equal for all of them, and the Cx will be equal for all the reflected rays. So they will actually meet at a single point, which is known as the focus, right? But for this case, actually, if we place a screen over here at say for example X, this will only be possible to have an image, a distinct image at point X for all the rays which are basically parallel to this principal axis and are actually nearer to the principal axis itself. See over here that these two rays, where this black and this red, they were much more nearer to the principal axis, and thus we could actually see a distinct image. Why? Because they are seeming to meet at a much nearer point, right? Whereas this was not the case for this blue and this red line. See, there is a wide difference between X and Y, right? So this is all about the concept of this focus, and we shall be learning much more interesting topics in the subsequent lectures, right? Thank you.